Good morning, Suzuki Science. This is grade 10, and we have finished cells. Last week, you guys did either a voiceover, or two of you joined me for a live presentation, and some of you just submitted the PowerPoint. I looked at some of them. I got a little bit of feedback on those PowerPoints you've submitted, and for the most part, I'm very happy with what you guys were able to produce, considering the conditions, the fact that we are not in class. A lot of this individual work, these type of presentations and end of unit tasks are typically very well done because many of you are able to work independently and ask for the appropriate help when necessary. All right, so now we are starting optics, and optics is going to be challenging for some of you. Some of you, we talked about this at the very beginning of the year, in that your math skills are not great. And without basic algebra, being able to identify and solve for x, for example, you are going to have some difficulty with the concepts in this class. So, at the beginning of the year, I had suggested that some of you who have difficulty with math and the algebra, that you practice the algebra and you practice working on, those very simple pre-high school algebraic skills. If you have not done so until now, then you're going to need to practice in order to have some success with this unit. In grade 10 optics, we focus on the physics. We do not focus on the math. But the math, having said that, the math is a critical skill in order to do and solve many of the problems that you're going to see in this particular unit, right? So this is how this unit is going to work. We have 5 sections of grade 10, and we're all doing the same thing. Ms. Dave, Mr. Martins, and myself, we typically have our own style of delivering lessons. In this particular unit, I'm going to be relying on some of the other teachers, and I'll be using, today, for example, this week, we'll be using Ms. Dave's explanation, because she's done an excellent job of putting together the math video lessons. I'm going to give a little prequel. I say little, it'll be like 25 minutes. And once I'm done with the prequel and some of the fundamental background terminology, what the week's going to look like, then I'm going to direct you to her PowerPoint from her YouTube channel, and then you'll work through the Google Sheet. So let's take a look at what's happening. Right now on my screen, you've seen the stepping feet motion illusion. What's going on? If I'm going to talk about optics, then it would, I think, be a good idea to talk about what it is that you see. So right now on the screen, I have these 2 bars going across, and when you look at it, it's kind of an illusion. As you stare at the screen, you'll see that they're going, well, what do you see? So this, if we were in class, I'd be asking the question and you guys would be responding and telling me. And many of you would be telling me that it looks like the yellow and blue bars are, if you look at them, especially if you look at the bars, if you kind of unfocus and just kind of glaze at the screen, you'll see something else, a different effect. But if you kind of look at the bars as they're going across, it looks like the yellow and blue bar are stepping, they're stepping across. Now, what I'm going to do is I'm going to remove the bars here and take a look. These 2 yellow and blue bricks are going equally. And now I'm going to bring these lines in. And as I bring these lines in, you'll notice a new effect. This is an optical illusion. Optical illusions are a lot of fun. So our brain is hardwired to allow us to take in all the sensory information we need to be able to skip a bunch of steps. If your brain is trying to process everything that it hears and everything that it touches and everything that it sees and every single sense inside your body, then it would be very overwhelming and you would not be able to process and work in the world as you currently are. So what happens is the brain does a lot of things where it just skips steps. It looks at the samples, a little bit of information, and makes some assumptions, and off it goes. And one of the places where you'll find a lot of tricks is in lines that are black and white, and swirls and curves, and the brain likes to finish things. It's a prediction machine. It predicts what the world is going to look like. If you guys go into higher sciences and you study psychology and neurobiology, you'll learn about the prediction mechanism of the brain. So we observe things, so the world is an observed, learned experience, but there's also things that we predict. And so a lot of times you think you see something, but you're not actually seeing it because your brain has just made a prediction and moved on. So this illusion is a classic illusion. Look at this. In this illusion, Again, because of the pattern of the blocks, these lines here appear to be growing bigger or smaller depending on if you look left or right. This is another optical illusion because of the way your brain is hardwired. If you're interested in this stuff, there's a lot of sites that explain it to you. We kind of explore a little bit of it in grade 12 bio as well. How about this one here? This screen has 1, 2, 3, 4, 5, 6, 7 by 1, 2, 3, 4, 5, 6, 7, 8. So it's got a 7 by 8 block. And if you look at the corners, if you look at any individual corner, you'll see that it's just white space. But if you kind of glaze away and look to the left or look to the right, you'll see your brain, what it's trying to do is trying to fill in the space, because that's what it does. It likes to fill in information. And so it's filling in the corners with these little black dots, which are not there, hardwired. Your brain typically is only able to master one schema. That means one image at a time. If you guys look at this image here, you might see the old lady, there's her chin. I'll give you a moment. You might want to pause it because I'm going to explain it so the video length is not too long. So I'm going to explain what you see here. There's an old lady, there's her chin right here, her mouth, her nose, one eye, her hair, and there's a young lady. There's her chin here, there's an eyelash, her little nose, and her hair, and a feather. So you might be able to see both of them. Maybe you can only see one, even though I explained it. And your eye's going to go back and forth, back and forth, back and forth. That's another property of your brain. This is a common illusion, the way the brain continues lines. So when you take a look at these lines, I know you won't believe me, but if you took a ruler and you measured this line on the left and this line on the right, you'd see that they are the same length. But you're like, there's no way. This is clearly on the right longer than one on the left. And this is another hardwired mechanism in your brain that allows you to, have you ever wondered how you're able to look at a picture and know it's a window that has depth? Because of how your brain is hardwired to interpret lines. We use that effect when artists are representing buildings and doors and things like that. Here's another one. So this is kind of psychedelic. You just stare at it for a while and you'll notice that even though this image is not moving on the screen, it appears to be moving because of how your brain is trying to complete the image. And so it ends up just shaking. It's not shaking. This is an image that's on the screen that's not moving. How about this one? Once again, you think it's moving. Like if you just look at any one area, you can clearly see it's not moving, but everything kind of in the peripheral is kind of rotating slightly. And when we look over there to see that it's not rotating, then it's just psychedelic. That's the word we use for this, psychedelic. And this uses another mechanism. Notice I use the word mechanism because I'm trying to avoid using all these fancy polysyllabic words that have 15 syllables inside of them to explain what's going on. If you're interested in this, then I encourage you to explore. That's what I'm trying to do. I'm trying to engage you in the science here. This one is very interesting. It's another mechanism. This one has to deal very much with your the optics, the optic neural biology and how you perceive information, how the brain completes this. So stare at the plus. You're going to stare at it for a little while, and what you'll notice as you stare at the plus that the purple dot suddenly turns into a different color. I'm not going to say what it is. Just say it out loud. Call somebody over. Tell them to look at it. Okay, look it away, and then look back. Stare at that cross again, and keep on staring. You'll notice that not only does the purple circles, dots, turn into a particular color, then suddenly something very interesting occurs. Okay, you have to stare at the plus. And then when you notice that interesting thing, that final interesting thing occurring, just look away and look back and you'll see it all appears. This is crazy the way the optics works in your brain. And this is another one. I encourage you. I'm going to ask you in some live meet that we're going to have later this week. Someone's going to tell me the name of this effect. So what you're looking at with this chart is you're staring at the words, right? You're going to read them as quickly as you can. So if we're in class, I'd say, all right, go. And then someone in the class, Mohit, I'll pick on you. He'll read. And so you have to read, you have to say the color. So this word here, it says yellow, but you have to say green. So you have to say green, red, blue. And you have to go through it as quickly as you can. And for many of you, because you're reading the word yellow, blue, orange, even though it's green, red, blue, there is a conflict between your left and right hemisphere because one processes color, let's say, and the other one processes language. And so the two of them are in conflict with each other. And so think about all the optics of that situation, processing color, processing language, and what's happening. We're just talking about optics. This is optics. We're focusing on the physics. But I want you to understand that even though we're focusing on the physics, it's not just about a single part of the science. It's not just about the chemistry. It's not about biology. It's not about the physics. It's not about the climate change. It's about science. So it all interrelates with each other. Okay? I rated that stepping illusion with you. Also on that same site, if I were to go back to it, there is, for those of you who like illusions, there's a ton of illusions on this site. Look at that, 138 optical illusions and visual phenomena. So I encourage you to explore this site. You'll see the link on the Google Doc. Okay, so that's our engage. That's you hopefully interested in this subject. Ooh, I want to make my own illusion. You totally can. This week, like the past weeks, you'll have your interactive Word Google form. And this Google Doc, it has several parts. So let me go over what it looks like. I've given you the minimum timing. So for those of you who only want to do the minimum, you're locked on that 3 hours and I'm done. Remember, that is highlighted in green. That green completion will have many gaps. If you're thinking about taking grade 11 sciences, physics, chem, and bio, and you've only done the green, you'll have gaps in your learning. It'll be more difficult. If you want to make sure the gaps are filled in, then you're going to complete the yellow. And this time, I haven't done it in past weeks, I've given you a purple, and the purple represents exemplary. This is the one where, you know what, you've cleaned your room, you've gone out and exercised, you've played with your little brother or sister, and you've watched the 14th Netflix show, whatever season episode you're on, and now you're like, what am I going to do? And you're like, okay, I'm going to do physics, I'm going to do optics. And so you go to the purple, and off you go, and I'll give you a very thorough, exemplary understanding, more like fun stuff. It's not really that fun, but stuff that extends the learning, okay? So in your timeline here, realistically, the green is pretty short, and if you work through it consecutively, it's probably going to be 25 minutes of video watching for part 1, 35 minutes of video watching for the real math, the real, I'm going to call it the real physics that you're going to find in optics here, the calculations. You're going to spend maybe an hour and a half to 2 hours answering questions and working through the worksheet. And that will bring you up to 2.5 to 3 hours, depending on how much time you spend on that. So that's your timeline. That's the minimum. If you decide to complete the yellow or the exemplary, you'll be spending more time. Okay, and it depends on your speed and how much you want to complete. On Friday, May 8th, you're submitting to me several things, like we've done in the past. This is now the beginning of optics. So your culminating task we'll talk about a little bit later. I'm not going to talk about it today. But you are going to submit this document. So this document, like you have in the past, you're going to work through it. There's places to answer questions. At the very end of the week, you hit submit, turn it in, whatever it is, done. You are also going to do a flip grid. And we've done this before, right? We've done it for practice. And I'm going to explain how this flip grid is going to work. In this flip grid, you are going to use it for me to determine if you're able to answer a physics question. Are you able to work through a solution? Okay, when I get to that spot in the lesson, I'll explain how to use it. Notice I've given you the example of minimum green, yellow is complete, exemplary is purple. The resources you'll find here are this video that you're watching right now. The part 2, I call it wave equation, that's from Ms. Dave, and you'll see a link to it. And the PowerPoints. There's more than one PowerPoint. I just said PowerPoint. Let me put an S there, PowerPoints. So as you're working through this document, anything that's lit up like a question, you answer it. Is light a particle or wave? You could probably answer this right now. And would you be right or would you be wrong? You'll have to watch the video to find out. What is a photoelectric effect? There's a YouTube link. You click on that and off you go and you watch it. You could watch 1 minute of the video. You could watch 3 minutes of the video. I think it's a 4-minute video. And then notice on exemplary, notes from the video. If you ever watch a video a teacher assigns to you, you always want to take notes, right? You always want to write down what is the overall theme of that video. At the beginning here, I've also asked you to give me the definition of light. We're doing optics. Optics. So we're looking at light and how light moves, how it reflects and refracts and moves through different materials. So you need to be able to define for me what is light. And I've given you several different definitions. Green, minimum. You need to know the textbook definition. And then there's other types of definitions as well. Other questions? And then when you get to this part here, this part where it says watch part 2 video, this is watching Ms. Dave's YouTube link. I have the link on both the Google Classroom and in here. This is probably the problem solving area and the most important part of the lesson, right? So this is the math. This is the critical skill. If you decide to take grade 11 physics, then this is the part you need to know, okay? And so it says work through the wave equation worksheet. So you'll see it scrolling down a little bit. And one of the sites that I'm going to give you as a support is called the Physics Classroom. And the Physics Classroom is an excellent site. It's designed for helping high school students, And when you go to the physics classroom, you'll see a link. On the left-hand side, you'll see a number of different concepts. We're going to go to light and color. And when you go to light and color, we are doing reflection eventually, refraction eventually, and we're also doing the understanding of light. What is light? What does light do? Okay, so there's reflection, there's refraction, but here's light. Wave-like behaviors, two-point source, thin, polarization. So there's some particular places on here that I'm going to direct you to. Lesson 1A, this is one of the first places. So this is a really good site. This could be in lieu of your textbook because they've done such a good job. And on here, they give you links to tutorials, to interactives, to questions you can complete to determine your understanding. It's very wordy. So you'll have to be able to read through the words. This is only to supplement your learning. This is not mandatory. This is supplementary. Okay, so that's your physics classroom. As you work through this, I'm also going to be giving you some Khan Academy practice. I like Khan Academy because they do a very good job of stepping you through solutions and stepping you through a process. The link to this particular Khan Academy video, along with some others, is not a video, practice is in the Google Classroom. This one is going to be exploring wave, speed, frequency, wavelength. This is the main formula that we're doing for this week. Right? It's an easy formula. You guys have done it in grade 9. We'll look at it in just a moment. Okay? Then we get to where it said, complete the wave problems activity. So this was all preamble. There are links to support you. You'll be watching the video lesson and then here are the practice questions. Remember, purple is exemplary. In class, we would have done this together as a class. These ones here, because they're easy, but they don't follow plug and play, right? With a formula, you typically plug in the numbers, you get an answer, done. These ones here involve a little bit more interpretation. And so we've decided as a grade 10 team that we're not going to do these, but you can give it a try. And there's lots of support in the videos, a lot of support in the video lesson, there's a lot of support in Khan Academy to try those, but leave them to the end. 3, 4, and 5. So these are the minimum. Everyone should do these. 6, 7, and 8. This is complete, so you're getting more practice. And that is the end of the worksheet. If you decide to do this worksheet and you submit it in the Google Doc, you type in your answers. If you're able to do your solutions, perfect. What I suggest is you could even write your solutions by hand and then take a picture and just embed it in this document. So that way you have a copy. This is not just for me, this is for you. So you have some kind of flow that you can look back at the end of the unit. Now, if I take a look at this next part, this is the week 5 PowerPoint. So there's a PowerPoint and you're going to work your way through it. I'm going to talk a little bit about it minimally because you don't really need me to explain the PowerPoint. You can work through it without me. I'm going to talk about the very beginning and then I'm going to be done. So when you work your way through the PowerPoint, this worksheet matches the PowerPoint. So as you go through the slides, it's going to give you a definition. It's going to say the operational definition of light is this. The eye brain is able to see this, and the electromagnetic spectrum represents this. And as you go through the PowerPoint, you can answer on this document. I wasn't sure how to do it, but these lines here, they're fill in the blank. So you can either highlight it and erase the line if you want, or type on top of it. It'll get longer, and then you just have to make it look nice, right? You decide what you want. It's for you, right? Even though you're submitting this, it's really for you. If it's green, it's minimum. If it's yellow, it's complete. So you decide what's most appropriate for you. When you get to question 18, I know a lot of questions, right? Question 18 is interesting, so let me explain how this works. Question 18 is a table. On this table, you're going to see 1, 2, 3, 4, all these different types of lights. And you've heard of some of these. Phosphorescent light. I said phosphorescent. What am I talking about? Fluorescence, chemiluminescence, you probably not have heard of. And these different types of lights, they get their energy from a particular place. The answers for here are on this table. So you're going to copy this. That'll be an answer. I'm not going to put it in the right spot. I'm just going to put it here. I'm going to paste it. Right? And then the example of what it might be, I'm just going to paste it. So these aren't right. I just did that to demonstrate what you're supposed to do. Right? And so the answers for this table are on the next page. I've given you a Learn 360 site. Now this is not like the Learn 360 resources we did in the last units in Cell, where it was just, it was really cool. It was interactive. You clicked on it and you're done. And you kind of took a screenshot at the end. This one here is more of an old school video. So you're going to watch that video from Learn 360. Let's see if I have it open here. Learn 360. I'm pretty sure I do somewhere. Learn 360. There it is. You can open up this video if you choose to do it. This is, again, it's just it's math, right? And a lot of you, I say the word in class, I really wish I could be there to, calm you down, to take a deep breath. This stuff's super easy. It's not, many of you work yourself up and out of the easiness of the concept. It's super straightforward, but we're giving you a lot of resources to help you. So this is a Learn 360 site, so it's a little bit different because you're watching a video and it's going to give you some explanations, all right? And the video is broken into segments. So here are the segments. And on the Google Doc that you're working through, I have taken the time to show you what those segments are here as well as here. Notice some are yellow and some are purple. The purples, unless you have the time at the end, skip them. The video quiz is great follow-up to consolidate the video learning, but again, I put it in purple. It's kind of the last thing you do because there's other things I'd rather you work on first before you work on that, okay? Here is a resource that goes along with the video that they're kind of true-false questions. So once you watch the video, you can see if you got them correct or not, and I'll post answers up later. And then at the end, I've once again repeated what you need to submit, okay? So coming back to that flip grid I was talking about a moment ago. So the way the flip grid works is, the flip grid is your demonstration that you understand how to solve a question. So if we go back to the worksheet that you're submitting in the main part of this, right? It says, watch part 2 video, wave problems activity. And then here's the worksheet in purple, green, and yellow. So any one of these 6 questions, pick any one. And then on the flip grid, what you're going to be doing is you're going to be taking your phone camera or some other camera device, and you're going to solve the question, and you're going to put it up on Flipgrid. No one else will see it but me. I will look at them, and I will see that, okay, you understand how to solve a problem. You don't understand, you need a bit more help, why don't you try doing this? You understand, and you could do this at any point during the week. Okay, and I'll be looking at it constantly. So I encourage you, once you've done the problem and you think you have success, then put it up. And then if a person does question number 3 and they do question number 3 accurately, then what I'll do is I will then make it visible to the entire class. And so if someone wants to do question 3 and they don't understand it, and someone did it properly and put it on Flipgrid, you will become the teacher. You'll become the tutor. You'll become the person that's able to help your peer in the class. So that's how we're using Flipgrid. So no one will see what you do initially. And if you don't do it correctly, don't worry, I won't open it up to everyone to see, just me. And if you do it incorrectly, I'll encourage you to take a look at such and such problem because they might have done it properly. Of course, we will help you. We're going to be posting up a schedule probably later on today. I guess today's Monday for you or whenever, at the beginning of this week. And between the 3 grade 10 teachers, we're going to have 3 live sessions. So we're going to have 3 times during the week where you could come in and meet with us live, and we'll work through any problems you have. Okay, so it'll be a live class. We're basically running a help session. So any of the math that you have difficulty with, we'll help you. During this live session, we'll also likely go over significant digits. And in physics, when you're doing calculations, significant digits is super important. It's very important. It's something that you really should be using from grade 10 onwards. Every time you do a calculation, addition, subtraction, multiplication, division, whatever it is, you should be using significant digits. But at this moment, I'm not going to go into that math. So that will be at the live class, and that will be posted in an announcement. All right? So that gives you an idea of what this week looks like. So you have the physics classroom as an amazing resource. You have the Khan Academy that you'll be using. You have Ms. Dave's universal wave equation video that you'll be referring to, which is 35 minutes long. And you have the flip grid that you'll be using at the end of the week. Also at the end of the week, like at the end of every week, there will be some knowledge questions. There'll be 5 to 7 questions that you'll have to answer based on some strict definitions, like what is the definition of light? Hint, hint, all right? So this first video is 25 minutes long already. So let's see if I'm able to finish off the next step. So the short port of this particular video, the learning, I'll be talking for about 10 minutes or so, and then we'll move on to Ms. Dave's video. The question is, what is light? So as you work your way through the Google Doc, you'll see the same question. This is a very interesting question. This is a question that they've been asking for a very long time. Many of you, I would like to say have taken math grade 10, but we know that, after March break, you've only done 4 weeks of math, so I'm not exactly sure what concepts you guys have picked up. But most of you should have heard of this guy named Pythagoras. He's from 6th century BC. So how many years ago was that? Right now we're in 2020. 6th century BC is 600 years BC. So 600 plus our 2020, that's about 2,700 years ago. That's how long Pythagoras was alive. And he, the ancient Greeks, try to answer that question. He proposed an answer. He said that light is a stream of particles emitted from a source of light, which is weird, right? We tell you when you define something, don't use the word to define the word. But that was his definition. Very smart person, right? The problem with that definition is that we can't see this light particle. Why not? Is it too small? Is it too fast? What's going on? We need more information. So that brings us over to Aristotle. Aristotle was 4th century BC, so a couple hundred years later. And he said light moved as a wave, like ripples in a water. So a pebble drops in, you see these ripples. Now the problem with waves is that waves have to travel through a medium. They have to travel through air or a liquid or something like that. And we know that the outer space outside of our Earth, between the sun and the Earth, there's nothing, right? There's absence. And there is no medium. And light can travel from the sun to the Earth. So that doesn't make sense. All right. So that's Aristotle. Another very smart person. I'm sure you've heard of him. So let's fast forward a lot of years, 1,000 years, 2,000 years, and we get into some other scientists you might have heard of. Newton, Isaac Newton, super smart. And he said it was a particle. You've never heard of Christian Huygens. He's one of the first people to make a modern clock. We used to use things like sundials, the ancient Egyptians, and we used water clocks, the Indians and Persians. And there's a lot of devices they use for telling time. And the problem with those devices was that they were very limited. They could only tell you an approximation of the time of day, but not the time based on a calendar or a yearly system. So Christian Huygens, in addition to his brilliance with physics, he also designed one of the earlier modern clocks. And he said that light is a wave. And so it makes sense. People agreed, people disagreed, and then we get to Einstein. And Einstein, he took all this information from before him, and he sat down for about 10 years working on these special theories of relativity and general theories of relativity. And before all that, he stated that he believes that light is a stream of energy packets called photons. And this is where I would suggest, as opposed to me talking, you watch this little animation. So you can watch the photoelectric effect. You probably figure out who that person is there. You watch this video, and in the video, you're going to see the same argument, and you're going to find out how Einstein was able to explain what light was. And on the Google Doc, you'll see that I've asked you to tell me what is the photoelectric effect. In grade 11, as a matter of fact, some of you might even design an experiment to show and demonstrate the photoelectric effect. So watch the video. I'll be back. I'm back. All right. Definition. What is light? Here is your textbook definition. A stream of photons that are massless particles, each traveling with wave-like properties at the speed of light. A photon is the smallest quantity of energy which can be transported. Notice there's nothing else on this page because it's supposed to be succinct. This is it. This is the star of this particular part of the show. This is your definition. The problem with this definition for most of you, it's like speaking, a different language. There's a lot of words there. They don't really have much meaning. And for many people, unless you study science, that meaning is lost. So here are some things about the light that you should know. Light travels in a straight line. So if you are standing on the other side of the door, and the door has no windows, and there's a window beside the door, I can't see you because the light cannot travel through the door. The light cannot go through the window and around the corner so I can see you. So the fact that light travels in straight lines is known as rectilinear propagation. That's a big word. And light does not need a medium to travel, which we thankfully know from the sun providing light to the planet Earth. Okay? And the last thing that I would like you to know is the speed of light is represented by c. You might remember Einstein's equation, E equals mc squared. C is the speed of light, 3.0 times 10 to the 8 meters per second. That's really fast. But despite how fast that is, it still takes us several years to get to their second closest star after the sun. At this point, what you would do, what my suggestion is, like there's a couple ways to run through this, is I start to explain what is light as a wave, the wave-like properties of light. So this particular PowerPoint, I gave you a screenshot. You can see it on the screen. I'm not going to open it. I'm not going to step you through it. At this point, this could even be a good point to stop this lesson if you want and move on to Ms. Dave's. If you go on to the second video lesson, the important video, the one that you should listen to, this is the one that focuses on this activity. Watch part 2 video, wave problems activities. You learn how to use the wave equation. You learn what the wave equation is. You learn how to use it, and then you solve these questions. Right? That's the most important part of the learning. So if you take anything away from this, that's what you want to take away from this. That's the problem. Okay? The things I've just talked about answer some of the questions up here. Once you've finished with that part of the video, or if you want, you can continue listening to this one, that's fine. This information here, I'm going to be talking about some of this here from the worksheet. The worksheet and the PowerPoint are kind of what I'm going to be going over next, but I'm going to do it very superficially, okay? Because there's really two major things I want to teach you. One is I want to teach you the textbook definition. You already got that. 2, I want to teach you the operational definition. So an operational definition is a simple definition that you might tell a person doesn't understand science. And so that definition is light is a type of energy our eyes are sensitive to. At this point, if we were doing this interactively in the class, I would have asked you, define light. What would you tell your little 6-year-old nephew or niece? And then some of you might say, it's what you see. Okay, that's kind of what we talk about. Light for us is different than what you might have for a pit viper that uses heat, or a bumblebee that uses ultraviolet radiation, things that we cannot see with our eyes. Our eyes are sensitive to the visible light spectrum, which we'll talk about momentarily. So this is the operational definition, and it's a really easy definition. Remember, light travels in straight lines. So if this is you, and this is the eye, and the eye brain, that's where our little friend here, wants to look at you, or you want to see the eye brain's feet, you need a straight path to see it. And unfortunately, you cannot see its feet, because going from its feet in a straight line would bring you up to your forehead. So this is a demonstration of rectilinear propagation. What you would see is the eye brain's eye, and then you'd see the brick wall, because the brick wall is in the way, and the light is unable to go through it. In class, if we were together, we would take a beam of light, we'd shine it through a prism, and I'd ask you, do this until you find the colors of the rainbow. Because one of the properties of a prism, it has the ability to split light into its component wavelengths. Red, orange, yellow, green, blue, indigo, violet. These colors of the rainbow are called the spectrum. And this is something that you talked about in grade 9 when you were trying to understand the properties of stars that are light years away. Just by looking at the light spectrum, we're able to determine what gases make up that kind of sun. So, I'm not going to go into much detail. I'm going to skip past this. Unfortunately, we're not together, so you're not going to get to play with the prism, but we are going to do a couple activities later in the week for our fun things, and I'm going to get you to hopefully split light and see these colors of the rainbow. So now, this is the last part I'm going to talk about. It's called the conceptual definition. The conceptual definition, the operational definition just helps a person understand what light is about, but doesn't give you any kind of detail. There's no science related to it. The conceptual definition explains the concept of light. To do this definition, we have to understand chemistry. Luckily, we've done chemistry. We did that at the beginning of the course. We were together, so I know you know these parts of the atom. So when I look at the atom here, at the beginning, I have my first level, and here I have, a second level. Here I have a second level. And out here I have the third level. So I have these 3 different energy shells. And remember, we're using a very simplified model of the atom. So there's electrons in the first level. We know that could be 2. There's electrons in the second level. We know there can be 8. There's electrons in the third level. We know there can be 8. And there's many more energy levels. So when energy comes in, what that energy will do is it will excite an electron. And the electron will bounce from the first level to the second or third level. So it might bounce up here. and the energy, it's super excited. Like something came in and it's like a punching bag, punched it, and it's got all this energy and doesn't know what to do. It's just, bouncing around, full of energy, full of energy, full of energy. And eventually what's going to happen, what comes up must come down. As it falls back down to its normal state, it releases that energy that was excited as light. That's right. So if there's a certain amount of energy that comes in and excites the electron only to the second level and it falls back down, that might be orange. Or if it excites it to the third level and it comes all the way back down, that might be red. Or is it the second level and it bounces up to the third level and it comes back down, that might be blue. So the electron, when it gets excited, it's up here, and as it falls back down, that energy is released as light. That is the conceptual definition. That is a definition of light that you really should know. That explains how light is produced. Okay? So on this graphic here, you'll see that I have other colors, other wavelengths of light, the other colors of the rainbow, and each of these are produced from different energy levels. So different electrons falling down from one energy level down to another. So blue is one, red is another, orange is another, green is another, and so on and so on and so on. You don't need to know which color is which, just the conceptual definition that when the electron falls down, light energy is released and you see it as light. Okay? So the question is that you should be asking yourself is, where did the energy originally come from? So the energy that caused this electron to go from this first level all the way up here, where did that come from? That's an excellent question. And in the bulbs that your parents and myself used, and still are used in many places in the country, that energy came from heat. So the incandescent light bulb has a very special filament, and as you pass electricity, a current through it, because it has such high resistance, it produces a lot of heat, and that heat causes the electrons to bounce up to a level and they fall back down, releasing light. So unfortunately, in the incandescent bulb, a lot of heat is produced. There's more energy used to produce heat than there is light, or it's pretty equal. And so you end up with a very hot bulb and a very wasteful process. But the incandescent light bulb is something that we've used for decades. Over the past decade, you've seen an influx of the fluorescent light bulb and the incandescent light bulb. And these light bulbs use different types of energy sources. So on the Google Doc, that table I showed you at the beginning, that is where you are going to explain how the different sources of light produce light and examples. And here's a list for you. So you're welcome to work through this PowerPoint, and in this PowerPoint I actually give you those answers. You could do your research if you like, you're on your own, and then you'll be able to answer that question. So after this, I just want you to work through the PowerPoint. I want you to be very clear and aware of what the electromagnetic spectrum is. The electromagnetic spectrum stretches from radio waves, which are super long, to gamma rays, which are super short. Radio waves don't have a lot of energy, and that's why you can be around them. And as you move to the right, you end up with more energy in shorter waves. Ultraviolet rays have enough energy that when they hit your skin, they cause your DNA to transform in a certain way that you might get melanoma, right? Dear 14-year-old me, you guys talked about this. X-rays were used to see what's happening inside your body, and that can cause cancers. And gamma rays do not produce superheroes. No X-Men, no Avengers, like you see in the cartoons and movies. Gamma rays, if you do get hit by them, generally melt your insides to goop. It's an unpleasant way to pass. This is what gets released during nuclear reactions or a nuclear meltdown. Right, so look at the electromagnetic spectrum. Also in the electromagnetic spectrum, you'll see a very particular part here called the visible light spectrum. And this is just a little segment, a little slice of the electromagnetic spectrum. So you should be familiar with the visible light, the part that we have sensitivity to. Our rods and cones allow us to see that light spectrum. But just because we see it doesn't mean other animals can't see other parts of the spectrum on the left or the right. And they can. Okay? I encourage you to use a mnemonic. A mnemonic is a device that allows you, it's a memory tool, so you often will take the first letter of each word and make a sentence or a song. And so many of you have the mnemonic for music. Every good boy deserves fudge, so you can remember the spaces or the lines. We use it in grade 11 biology. Does King Philip come over from Germany swimming? I'm sure there's many others that you might use as a tool. So I would encourage you to use a mnemonic to help you remember the electromagnetic spectrum. So once again, work through the PowerPoint. Other key features are explained to you in the words, and If you work your way through this PowerPoint, you will have a okay understanding of optics to get started. So I'm just going to click through here so you can see it in this video, but you're going to actually open up the PowerPoint and go a bit more slowly. Some of these concepts you learned in elementary school, some of these concepts are relatively new. You'll need to know some of these concepts in order to understand what we're doing next week. I will leave you with these. These things are crazy, right? You might have seen them before. They're called the magic eye patterns, and it's a stereographic image. So in this image, if you stare at it, there's a tool, there's a technique for doing this, not a tool. And if I look at this image and I look very carefully, if I'm able to relax my eyes or look past the picture to a place that's a foot behind the screen, I can see this image just pop out. Not everyone can do this initially. It does take a little bit of practice. I have a whole book of these, and I might take a couple of screenshots and put them on and see if you're able to see what is actually in here. So some of you will be able to do it. Some of you will think or do it, and you see like a whale or something like that, and others of you will actually be able to do it. So I'd like to know what image is hidden behind this magic dot.